Okay, so we are looking at rank of sets of vectors. And if you look at the definition, we say that for rank of set of vectors, it is the set of n-dimensional or the maximum number of linearly independent represents the rank of a set of vectors. We are looking at trying to show that they are linearly independent. Then after that, the focus now is to count the number of linearly independent of the set of vectors given. And as we learned earlier, with trying to prove the linearly independent, all that you have to do is to form a linear combination of the vectors given with some scalars, unknown scalars, and then equating it to 0. So if you're able to go through that process and then get the unknowns to be zeros, you are now going to count the number of unknowns that gave you 0. And those numbers will represent a corresponding set of vectors. So you count those vectors, and then those vectors will now represent the rank of the set of vectors or the matrix. So let's look at the first example, and as we go through that, more understanding will come. So we would have to, so you can see that notes, rank of matrix is the number of linearly independent columns in a matrix. So if you're able to change the matrix to RREF, all that you have to do is that you are going to count the number of leading terms or leading ones in the columns, and those will now represent the number of rank of the vectors. Or you can also count the number of non-zero rows in the vector or in the matrix. So let's look at the first example. Given that A equals 25, 64, so we have A, the vector is given, B, the vector is also given, and then we also have C, vector also given. So we have to find the rank of this set of vectors. So let's see. So the solution is that we have to go through the processes of finding linearly independent set of vectors. So all that you have to do is to form a scalar multiplication of the vectors with some unknown set of scalars and then equating it to 0. Now you can see that the matrix has been transformed into an augmented matrix, or the set of vectors has been transformed to an augmented matrix. So you go through the process to the final level, which is the RREF. So you can see that we have written finally. You can see that finally, this now represents the RREF. So if you go through the processes and you get to where I've written finally, it will just change to a 3x3 identity matrix. And then you are now focusing on getting the unknowns. So you realize that if you check the unknowns, X is equal to 0, Y also equal to 0, and Z is equal to 0. So you can see that once the unknown scalars are all 0, it means that they are linearly okay. So finally, when you're able to get, if you're able to get the identity matrix, you are now going to check for the unknowns. So realize that X, Y, and Z are zeros. So what it means is that all the set of vectors are linearly what? Independent. So you are just to count all the set of what? Remember that the rank represents the maximum number of linearly what? Independent. So once all the vectors are linearly independent, we are now just going to count the set of what? Vectors given. And you can see that the set of vectors are 3. So therefore, it is what? The rank of the matrix is what? Is 3. Because it's the maximum number of linearly what? Independents in the rank of the vectors. So to find the rank of the set of vectors, complain they can see it's not a small working. Okay, so after you let me continue. Okay. So after you've been able to identify the unknowns that gave you 0, it means that if 2 of the unknowns are 0, it means that the rank is going to be 2. It's not going to be 3. But because all the unknowns so what's the problem? Okay, so someone is saying that they can see. So let's make progress. Thank you. Okay. So we realize that all the unknowns are giving us zeros. So it means that all the set of vectors are linearly independent. So yours is just to count the set of vectors, which is 3. So it's a 3 by 3 what? Matrix. So the vectors are also 3. So that is all. It means that the rank of the vectors is going to be 3. Assuming that only x and y gave us the zeros, what it means is that the rank of the matrix or the set of vectors is going to be 2. It's going to be 2. So you take notes of that. You take notes of that. There are those set of unknowns that gives you 0. That forms the rank of the matrix. So this is a 3 by 3 and all of them give us 0. So it means that the rank is going to be 3. Okay, so let's make progress. Okay, so let's take another example and then we see. Let's take another example and then we see. Now with this one, we are also to find the rank of the set of vectors. You can see that we have A, we have B, C, and D. These are the set of vectors that is given. Someone say that should solve it on the board. No, I'm not going to solve it on the board. So you listen carefully and look at it. That is all that is here. I don't need to solve anything on the board. All the processes that are involved with this is the RREF. And then we've gone through that. We will not waste our time going through the RREF processes. So you take note of that. Okay, so maybe I'll just give you the PDFs after the class. So you listen and then those that can manage and see, you manage it. So that after the class, I will share with you. Those that are saying they want to record, later it will be given to you. So you manage it. And so listen and they understand. And let's make progress. So you can see that if you look at this set of vectors, you can see that there are 4 set of vectors. And as such, if you want to form the augmented matrix, the maximum, remember, the rank is the maximum number of what? The set of what? Linearly independent. So you can see that this set of vectors will form a 3 by 4 matrix. So you do that. So as you can see, you multiply the unknown scalars from X, Y, Z, and W. They are representing the unknown scalars. And then you go through and see if you can be able to form the augmented matrix. But you can see that with the rank of a matrix, it should be less than or equal to the dimension. The rank of a matrix should be less than or equal to the dimension. So if you look at this set of vectors, the dimension is in what? R3. The dimension is 3. So there's no way we can form an augmented matrix that will pick 4. It's not clear. Yeah, it's not going to be easy. So you manage it. I'm trying my possible best for it to be clear to you. But because I'm holding it, it's shaking. I've also tried with the selfie stick, but that one two people are complaining. So let's manage it. Later, I will share it with you. I will share the documents with you. So don't worry, you listen and let's make progress. So you realize that you cannot form an augmented matrix with all this set of vectors. So the maximum number of matrices you can form is a 3 by 3 what matrix. So you can pair 3 vectors at a time. If you want to form the augmented matrix, you can only pair 3 of them at a time. You can only pair 3 of them at a time. So remember that if you look at the first 3 set of vectors, that is the previous question we solved. The first 3 set of vectors is the example 1 we solved, and all of them was linearly independent. So what it means is that it is the only 4th vector, the D, that will not be linearly what? Independent. So as such, what it means is that the rank of the matrix is going to be 3. The rank of the matrix is going to be 3. So if you want to prove that, all that you have to do is to pair 3 of the set of vectors at a time and find the unknowns, the number of unknowns that are giving you 0. So if you realize that if you pair all these set of vectors, it is only 3 of them that is going to give you what? Unknown to be 0. So let's make progress. So you can see that, yeah, someone is raising the hand. I know that it is not that clear, but let us manage it, okay? Let us manage it. Okay, let's make progress. So you realize that you can see that the dimension is 3, because understand that the rank of the set of what vectors should be less than or equal to the what? The dimension of the vectors. So the dimension is 3. So there's no way we are going to get a rank to be 4. There's no way we are going to get a rank to be 4, in a sense that the set of vectors that are given are in R3. In R3. And we are saying that for rank of set of vectors, they should be less than or equal to the dimension of the set of vectors. So that is why our R cannot be 4. So what it means is that we would only have to pair this set of vectors 3. So we can only form a 3 by 3 augmented matrix and find the unknowns. So if you do that, you are going to get only 3 of the vectors to be linearly independent. And the number of linearly independent set of vectors forms the rank. So yours is to just count the unknowns that gave you the zeros, and then their corresponding vectors will be counted, and it will represent the what? The rank of the set of vectors. So that is that. So in this example, there are 4 sets of vectors given, but you can see that all of them are in R3. So the maximum rank of the vectors can be 3 or below. And if you check the pairing, it is only 3 of the set of vectors. That will give us unknowns to be 0. Someone is saying we can't even see. Okay, so let's make progress. So with this second example, we can only pair 3 of the set of vectors in an augmented form and then find the number of unknowns to be 0. So if you go through all these processes, only 3 unknowns will be 0. So therefore, the rank is going to be 3. The rank is going to be 3. The rank is going to be 3. Someone is saying, please, why not using the board? We are not using the board, please. So manage it. Because the camera, this thing is also not helping. Okay. Okay. So let's make progress. Let's look at the third. Let's look at the third example. Let's look at the third example. Can you see now? Can you see now, please? Can you see, please? I'm now using the board. Can I carry on? Okay, okay, okay. Okay, so let's make progress. So let's take the third example and then we look at that. So we are to find the rank of this set of vectors. We are to find the rank of this set of vectors. So this is a matrix. So what it means is that the vectors has already been in the form of a matrix. So you can either find the rank of set of vectors or the rank of what? A matrix. Now this is in the form of a matrix. So straightforward, all that you do is to go through the process and turn this matrix into RREF. So if you are able to do that, you realize that it will change to 4, 6, so we are going to augment this matrix. So what I do is that you write the matrix and then you augment it with the what? The 0 vector. Because this is what? A 3 by 4 matrix. So we can see that we can get a 3 by 3 matrix out of it. So it means that our 0 vector must be 3. So you augment it with a vector. And then when you go through the RREF process, all that you have to do is to get the leading ones for the set of columns. So those that will give you the leading ones, you just count them, and then that will represent your rank for the set of vectors. So finally, when you do this, you realize that only two of them is going to give you a leading one. Only 2 of them is going to give you a leading one. We cannot go through all these processes. So go through that, the process of the RIF, only 2 of them will give you a leading one. So what it means is that the rank of the matrix is going to be 2. The rank of the matrix. So when you go through this set of matrix that is given, the rank is going to be 2. So go through the RREF process. You realize that only 2 of the columns will give you the leading one. And as such, it will form the rank of the matrix. So the rank of this matrix is going to be 2. The rank of this matrix is going to be 2. Okay. So let's make progress. Now, let's move to solve more examples. Let's move to the basis of set of vectors. Basis of set of vectors. We are looking at basis of the set of what? Vectors. Now, given set of vectors, how do you find the basis of those vectors? Now, there are 2 things you have to satisfy. There are 2 conditions that must be satisfied for set of vectors to be what? To form the basis. So what you do is that you have to show one. You have to show that the set of vectors. You have to show that the vectors are spanning. First, you have to show that the vectors are spanning. The set of vectors are spanning. And then secondly, show that vectors are linearly independent. So these are the 2 conditions that makes set of vectors form the basis of some other set of vectors. So what you do is that first, you have to show that the set of vectors are spanning. The set of vectors that will form the basis are spanning. Then secondly, you also show that the set of vectors that will form the basis are linearly independent. Someone is asking that what are spanning? What are spanning? Okay. So when we talk about spanning of set of vectors, what it means is that it should form a linear combination. We have looked at that. We have looked at spanning of set of vectors before. So if you revise, you would have gotten it. It is just to show that those sets of vectors that will form the basis are forming a linear combination with some scalars, with somewhat scalars. So that is that. Then the linear independence. The linear independence. All that we have to do is also to form a linear combination of the set of vectors with some scalars, unknown scalars, and then equating it to what? 0, the 0 vector, and equating it to 0 vector. And then also go through the RREF processes again and find the unknowns that will give us 0. Those unknowns that will give us zeros will now represent some set of vectors. So the vectors is augmented in order. So let's take an example. When we take the example, I can now use that to explain so that we get it clear. So let's make progress. Let's make progress. So we look at the first example. Let's look at the first example. Okay, so the question is, do the set of vectors that are given form the basis for R3? So the R3 is representing the dimension. The R3 is representing the dimension. So you can see that it is having X component, Y component, and the Z component. So you can see that all the set of vectors are in R3. Okay. So first, we are going to show that the set of what? Vectors forms linearly what? Independent, or they are linearly what? Independent. So let's look at that. So the solution. So to be linearly independent, then AU plus BV plus CW should be equal to what? 0. So for this set of vectors to be linearly independent, then AU, so the U there is representing the first vector. The V there is also representing the second vector. And then the W is also representing the third vector. Then the A, B, and C are the unknown scalars. And it should be equal to the 0 what? The 0 vector. It should be equal to the 0 what? Vector. Okay. So if you're able to go through this process, so we are going to augment the set of vectors, and then we now see the unknowns. We are going to find the unknowns. We are going to find A, B, and C. Which of them will give us 0? So those that will give us 0 will now be traced. We can see that the scalar here is for the first vector. The second scalar is for the second vector in that order. So our augmented matrix is going to also form in that order. So that if you are able to get the zeros, scalars, you can be able to trace those set of vectors that give you the zeros. And those are the set of vectors that will form the basis. Okay. So let's augment the matrix. We are going to get 1, 0, 1, 0, 1, 2, 1, 1, 2, 3, and then we augment it with the 0 vector. We augment it with the 0 vector. So that is that. So we are going to change this or transform this what? Augmented matrix to RREF. So we see that the RREF is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. And then we are going to get the zeros. So if you go through the RREF processes, this is what the matrix here will change to. You are going to get this to represent your RREF. You are going to get this to represent your RREF. So in conclusion, it means that your unknowns A is going to be 0. So this is your A, this is your B, and this is your C. So A is going to be what? 0. B is going to be 0, and C is also going to be 0. So once all the scalars are 0, we are going to trace this, the first column. So that is for A. So what it means is that it is for this vector. So what it means is that this vector can form a basis because we have gotten 8 unknown or the identity matrix. So it means that this will be 0. So you trace it to the vector. that is corresponding. That's the first vector. So what it means that the first vector will form a basis. If we trace this one too, we're able to also get the leading one there. And as such, it also gave us B to be 0. Trace that, it will also come to the second vector. So it means that the second vector too will form a basis. Then the third one too, we had C to be 0. If you look at the C column, it has also formed a leading one in the form of a column. You trace that column, it will also trace it to the last vector. So you can realize that all the set of vectors are linearly what? Independent. They are linearly what? Independent. And since they all also have a leading one in the form of a column, all the columns are having a leading one. And it also gave us the unknowns to be 0. So once the unknowns are 0, it has satisfied the condition of linearly what? Independence. And then we are looking at the spanning. The spanning to, you see, when we initially express it in the form AU plus BV plus CW, that also satisfies the what? The spanning of the set of vectors. The spanning of the set of vectors is just looking at you trying to be able to what? Express the vectors in the form of a linear combination. And a linear combination is the scalar multiplication of set of vectors with some unknown scalars. So that spanning condition has already been satisfied from the beginning of our statement. So you can realize that in the process of going through linear independence, that is writing your scalar multiplication of the set of vectors and equating it to 0. The left-hand side alone satisfies the spanning. So you don't need to show any spanning condition again. You don't need to prove any condition for spanning. The process of linear independence, the left-hand side of it satisfies that it spans with a set of vectors. So once you're able to go through the set of linear independence proof, and you get the unknowns to be 0, we are looking at those set of what? Unknowns that give us 0. They will form the basis. So you just trace their columns to the respective what? Vectors given. And so assuming that A and B only gave us the 0, what it means is that it is only A and B that are linearly what? Independent and are also spanning. So you trace them, and if you trace them, what it means is that it's going to be the first and second what? Vectors that will form the basis. But because in this case, all the unknowns are giving us 0, what it means is that all the set of vectors too are satisfying to be linearly independent. So that condition is satisfied. And they are also what? Spanning. So that is that. So all that, so the clue here is that you are looking at the set of unknowns that will give you 0s. And then you trace them to their respective what? Vectors. And those are the vectors that will form the basis of the other set of vectors. So you see that the vectors may be many, but only few or sometimes all of them can form the basis. All of them can form the basis. Or only those that are given the scalars, unknown scalars to be 0. Their corresponding vectors forms the basis of the vector. So that is that. And it spans in R3. It spans in R3. So that is that. Okay, so let's take the second example and look at it. Let's look at the second example. So let's look at the second example. If you have okay. So look at this example. You see that there are so many set of vectors, and we have to find the basis of this set of vectors. So the vectors can be as many as will be given, but the focus here is that we are looking at those ones that when we form the augmented matrix, those that will going through the process to the RREF, those that will give us the leading ones. We trace that columns to the vectors and then choose those set of vectors to be your basis or to form the basis for this set of vectors. So let's look at that. So if you form the augmented matrix, it's going to be like this. 1, 2, 1, negative 1, negative 1. So because we are looking at basis, we are looking at what? Linearly independent. So we bring the 0 augment it with the 0 vector. Because it's in R3, all the set of vectors are in R3. So your 0 matrix will be 3. If they were 2 in R2, the zeros will be 0, 0, to not be 3. So if it's also 4, R4, your zeros will also be 4. Okay, so that is that. Now this is the augmented form. So you are going to reduce it. So you get to RREF, the reduced row echelon form. The reduced row echelon form. So if you reduce that to that level, those that will give you the leading ones, you can see that you can trace them to the original vectors. You can see that it is arranged in that order. The vectors are in order. So your matrix, the augmented matrix too, must form in that order. You don't change them. So that when you're able to get those that give you the leading one, you just trace them to the corresponding column matrix, the original matrix, and then pick those set of vectors as those vectors to form your basis. So that is that. And then you can see that this will now prove to show that. So those that will give you 0. So at the end of the day, those that will form the leading one, what it means is that the unknown scalars of such ones are zeros. So it means that the linear independence will be satisfied. Then the spanning is just going to, we can represent numbers, set of variables to represent the matrix or the vector given. Sorry. So you can see that the spanning will be okay. So let's finish with the linear independence. When you get here, reduce it. When we reduce it, this is how the RREF will look like. This is how the RR will look like. To just change to 0, 0. Then we have 1. Okay. So when you reduce, we see that you get only 2 of them to give you the leading one. The first one will give you a leading one. The second one, the second column also give you a leading one. The rest, you cannot get a leading one there. So what it means is that their corresponding set of of vectors will not give you will not form the basis. So you are just going to focus here. So what it means that you pick the first vector, it is going to form a basis. You also pick the second one, it's also going to form a basis. So it means is that your conclusion will be So only the first vector and the second vector will form the basis because they were the ones that gave us the leading ones. So you trace them, and it's only the first two that will form the basis for all the set of vectors that was given. So that is that. And as I said, if you also want to show the spanning of the set of vectors, you can represent all the vectors by variables and then the unknowns also by variables. So you can write that for the spanning, so for the spanning, will be A1 of U plus U2 of B plus yes, so should be equal to 0. So you can always start with this one first before the linearly independent. So this, the U, V, W, X, Y, and Z are representing the set of vectors. So we have identified, or we have named, we have given what? Some variables to represent all the set of vectors that was given. And then the A1, A2, up to A6 represent the scalars. So once you're able to express it and equate it to the 0, this is proving the span. Once you have established that this is a linear combination, and it should be equal to the 0 vector, the spanning condition has been satisfied. Then from this, you can now what? You can now prove the linear independence. So this one can always be written first. Then you go through the augmented form, and then you now find the linear independence, the unknown scalars, which will give us the leading ones. Then the leading ones, we realize that this and this, that only give us the leading one. So the two condition has been satisfied. So you conclude that it is only these two set of vectors that satisfy the two conditions, and as such, they are going to form the basis. So you conclude that therefore the basis for the set of what? Vectors are that and then what? And that. So these two are now representing the basis for the set of what? Vectors. Someone is asking, why do we not have to know all this? Please, let's focus and continue. Okay. Okay, let's look at the second example. When I finish this, I'll give room for questioning. Then we'll carry on. Okay. So now let's take the second example. Okay, so I think this is the second example. So that's all. Let's move on. And then we look at the last one. And then we will now give room for question. Let's carry on. Let's look at dimension. Let's look at dimension vector space. We are looking at dimension of a vector space. The dimension of a vector space. Okay. Now, the dimension of a vector space V is the maximum number of linearly independent elements in V in the set of vectors. Or in other definition, you can say that the dimension of a vector space is the number of vectors in the basis of the space. So what it means is that after you have found your basis, as you have done already, you just have to count them. So instead of you to write the vectors that, as we did earlier, those two vectors represent the basis. You have to count them. So you see that you now conclude that the dimension is just 2. So the dimension counts the number of what bases. That's all. As simple as that. The dimension counts the number of bases. You know, the bases are written in the form of vectors. So you are there writing the vectors that forms the basis out of all the vectors given. Then dimension is saying that count them, count the number of bases. That's all. So after you've gotten your basis, or that if they ask for dimension, what is the dimension of the vectors? It is just about counting your basis you found in the set of vectors. So if you look at the just ended example we solved, we had the vectors. Let me look at it. We had the vectors 1, 2, 1, and -1, -1, 1 to be the what? The basis. So these were the 2 vectors that form the basis. So all that you do is to just count them. So therefore, the dimension is 2. The dimension is 2. Then if you look at our first example, where we are looking at the basis, you see that we had all the set of vectors to form the basis. We had all the set of vectors to form the basis. So in that case, you write that the dimension is what? Is 3. The dimension is 3. So dimension is just counting the number of bases, or the number of what? Vectors that formed the basis. So that's all. Let me add this example and then we just conclude. Let me add this example. Just conclude. So we are using this as our third example for the dimension, because all that you have to do, we are using the 2 examples we did under the basis and just writing the number. And the number is just the dimension. So we are just starting with a new question. And that one is going to be the third example. So that's all. So you use the basis examples and just conclude, just count them, the vectors. When you count the vectors that are representing the basis, that is your dimension. So let's take the last example for dimension. So let's okay, so this time around, there is what? A matrix that is defined for us to be what? W. So the definition is given that this matrix is formed by A, B, B, C. This matrix is formed by A, B, B, C. And they are saying that A, B, and C are a member of real. So A, B, and C can be any real number. A, B, and C can be any real number. So let's start. So what it means is that we are going to form some set of what? Matrices that from this word definition, we are going to form some number of what? Matrices. And then after you have done that, so this is the vector definition, the matrix definition that is given. We are saying that we can form any matrix by this definition, said that we can pick any number to represent A, B, and C. So any real number, A and B and C, can form a matrix out of this, said that A, B, and C can be any real number. So we are looking at how, or the dimension we can get from this what? Vector. So you can see that if we choose to make A to be 1 and then the rest to be 0. Okay, so let me do that. So when A is 0 and then B is equal to C is equal to 0. When I make A to be what? I'm making A to be 1. I'm just assuming any what? Scalar. Please, the lights out. Please, can't you see? Please, let's continue. So I'm saying that if I make A to be 1, you can't see. I think it's clear. So please, let's manage. Okay. So if A is, okay, let me write it well so that I can see more. So if A is equal to 1, B equals C is equal to 0. If we assume A to be 1 and B and C to be 0, look at the definition of the matrix. A, B, and C can be any real number. So we are going to form set of what? Matrices. With this what definition? With this definition. So let's look at how we can form a matrix when A is 1. When A is 1. So when A is 1, you can see that we can form a matrix 1, 0, 0, 0. You see, look at that. When A is 1 and B is equal to C is equal to 0, we are making all the rest 0, and then only A to be 1. It will form this matrix. So that is what? 1. We can see that we have formed a 2 by 2 matrix out of this definition. So that is 1. Let's look at also making B to be 1 and then the rest to be 0. So if we also make B to be 1 and then A equals C equals 0. If we make A to be 1 and then we make A and C to be 0, it's going to form 0, 1, 1, 0. So you see, if we also make B to be 1, it is an assumption. You can pick any number. You can pick any number to represent all these words, numbers. So I'm choosing that when I make B to be 1, the rest should be 0. And I see the matrix that will be formed. You can see that it's still a 2 by 2 matrix. It is still a 2 by 2 matrix. So you see that it is spanning or the linear independence. When you factor A out, you see that I get the 1, 1 and then the 0 out. So that's that. So let's make progress. Then the last one, if I choose to make C to be 1, if I choose to make C to be 1 and B and A to be equal to 0, that one to form a 2 by 2 matrix. So A 0, B also 0, and then C to be 1. So you see that we form these 3 matrices, which is also please, that's how it will be. Let's manage, okay? Please. So let's manage. So you can see that we have formed 3 2 by 2 matrices, and they are all in the definition. The definition is to form a 2 by 2 matrix. You can see that all of them are 2 by 2 matrices. So now the scalar or we are looking at the what? The linearly independence. The linearly independence. So you can see that when any of the numbers, so any of the numbers, one is 0 and the other is 1, we form this one. So it means that it is what? It is within the definition. It is within the definition. And then the scalars will be, we can represent this by maybe say V, U, V, and then W. U, V, and then what? W. So if you look at the real definition, you can factorize the numbers out. So if you choose to factor A out and make the rest 0, it will form the what? The linear combination of this set of what? Matrices. So if you factor A out, you can get and make the rest 0. You see that you are going to get something like 1 and then 0, 0, 0. You see, when you factor the A out, then the rest to be 0, you get this. So you realize that it will form. Then you can add the set of what? Matrices. If you add all the set of matrices, that is going to be the scalar what? multiplication of the set of vectors, and it's going to prove for the spanning. So if you're able to add all these vectors, you can see that it will still be in what? In what? A 2 by 2 matrix. So if you add all the three set of what? Of matrices we have derived from assuming values for A, B, and C, it is still within what? A 2 by 2 matrix as it is defined. So it makes it to be what? To be spanning. And then for linearly independence, we're saying that we should be able to what? To generate what? It should be able to generate the zero what? The zero vector. And you can see that the zero vector 2, which is the identity of a 2 by 2 matrix 2, it can be generated. If you assume all of them to be zero, you can still generate that one. So it means that all the conditions, and it forms the 2 by 2 matrix. So you see that all the conditions are satisfied. Then yours is to count. As I said, you have to count the number of what? Bases. And once all these three form the basis, you see that in the definition, we are going to get A, the second comma, B, comma, C. It's a member of what? Real. So you can see that it has formed a 2 by 2 matrix. That's what? 3. We have gotten 3 2 by 2 matrix. So it means that the number of what? Or the dimension is what? Is 3. The dimension is 3. So that is all. So you are just to count them. So you just write them. So these are the bases. So these are the bases that will form. These are the bases that will be formed. These are the bases that will be formed. Then we also had 0, 0, 0, 1. This is another one. And then we can add which one again? Yes, we can also add this one. So that is that. So that is that. So you see that that's all. Then so you see that this has formed the basis. This has formed the basis. When we assume numbers for A, B, and C, we had this set of what? 2 by 2 matrix, which is forming the basis. And dimension is saying that count the basis. Dimension is saying that count the basis. So we just have to count them. There are 3. So it means that the dimension of the set of what? Definition in W is what? Is 3. So that is all. That is all. So I'll now give opportunities for questioning. If you have any question with regards to all that we have looked at, you can now ask your question and then.
With the dimension.
We have the dimension, okay.
The number of bases.
Please speak louder, a little louder.
You said we had 2, right?
You said?
You said we had 2 for the dimension. We had 2 for the dimension.
Yes. Is it for the matrix?
Yeah, yeah.
No, the matrix is going to be 3. But we're able to form a 2 by 2 matrix of what? Of 3. We form 3 2 by 2 matrices. So those are the basis. So you just count them. So they were 3. Are you okay? Any other question?
I'm talking. So you said the first one. You said the first one is sir.
Is there any other question?
Yes, sir.
Yes, please,
sir.
Your question.
I'm talking of the basis.
Okay.
How you got the basis?
How I had the basis?
Yeah, with the first one, you had with the first one you had 1 0 0 1.
Okay.
How did you get that first one? Like the first one.
Okay, you just assume any what real number for the numbers, for the variables, yes. A, B, and C.
Yes, sir.
So I just chose to make A to be 1 and the rest to be 0. And then to form a 2 by 2 matrix.
So about with the first one, you had C to be 1. That's with the first one, the first basis.
I had C to be
1. You wrote C to be 1. Like
yes.
After you were done with everything, it's on the board. It's
okay. So I think that after I did everything, I was supposed to arrange them. So the C, the one I made C1 and the rest 0 was the last one. So
okay,
the
so then with
arrangement
that
will
one,
change.
so then with that one, you made A to be 1 because when you look on top, we had 1. 1,
Oh, okay.
0,
So it's supposed to be 0, 0, 0, 1.
Okay.
So if there's a mistake there, you correct that.
All right.
Okay. So it's supposed to be 0, 0, 0, 1. For the C, making C to be 1, and then the rest to be 0.
So then with the next one.
Which next one?
The next basis. That one to C is equal to 1. It's on the board. I don't know if you can see. Okay, it's on the board.
Okay. Oh, okay. So I think, okay, let me check.
So I think you cleaned the first and the second one before you got there. So it's like he couldn't get that place. That's why. But when you did the first one, you cleaned that part. And so this was the last part that was actually there. But the down one that you are not doing is when you finish, we're now compiling them. So I think that is why.
I think I didn't check it too. So it's just, I think 1 will be 0, 0, and then 1, 1. Yeah, so it's just the compilation that's brought the distance. So you can just check that and then do it. I hope you are okay now.
Yes, sir.
Okay. Any other question?
Police, sir.
Okay.
Yes, sir.
Yes, please. Your question.
My question goes to the last example. The last example you worked under the basis that involves 6 vectors. No?
Okay.
Actually, that example I didn't get it, so I don't know whether you can go through that one again.
Okay, so all that we have to do is that you go through the RREF process. I hope that one you are able to do that already. You are just going to change the augmented method to RREF. When you get there are some that you cannot change to a leading one. You see, so those ones that you'll be able to get the leading ones, they will now form the basis correspondingly. So you see that the matrices, when you are forming the augmented, it follows that order as it has been given. So you trace that column that gave you the leading one, and those set of vectors will form the basis. So you realize that only the first 2 that will give us leading one. When you go through the RREF, only the first 2 will be able to give you a leading one, and those vectors will form that corresponding vectors will form the vector, the basis. Form the basis. Any other question?
Thank you very much. Okay.
So a quick follow up on that same question.
Okay.
So I want to find out, let's say in exam sake that a similar question is given. Can you just look at the 6, 5 vectors there, and then you say maybe 10 can go, or you have to work all that before you can now come and conclude?
Yes, without going through up to the RREF, how will you be able to get the basis? It is not going to be easy. So it's through the RREF you can get.
That's not easy.
Yes.